hand on. Yes, this is the unsupervised. So I've not yet put this script on GitHub, but I'll do that at the end of the class. However, I can share the script with you guys to open in your end. If you have Jupyter Notebook, of course, you could be able to do that. So let me go to the WhatsApp group and see documents. Okay, so I have shared it in the group. You can download it, but I will put it in the GitHub immediately after the class. So that way, I think you will not have issues running it. And all the data set we are using, also it's easy for you to find it because it's skitlearn data set. So for now, I've not started pulling some data set from Cargo, but we will do that when we start looking at the complex cases. So the first thing we are going to look at is the dimensionality. In fact, the practical section today will just be for dimensionality reduction. I didn't want to bore you with all the clusterings because I was really kind of considerate. So probably next week we'll continue with the clustering hand-on sections. But I think it was a good thing that we deal with the theoretical parts today, so we don't have to reinvent the wheel next week. So the first thing we said, principal component analysis. Remember, we said we try to build linear combinations, and then we project it into a lower dimensional plane for us to be able to see it. And then we talk about the T-distribution stochastic neighborhood embedding, which is the tSNE, where we said we've also tried to find local minimals. We find those local structures, different from the PCA, because the PCA assumes linearity, but the tSNE, they are non-linear approaches. Then we also talked about although I didn't emphasize lots on this, but I said the manifold or the uniform manifold approximation and projection, or UMAP. It's also an extension of the PCA of the tSNE, sorry, where we looked at this approach offers an alternative that is both fast and capable of preserving global structure and also local structure. So, PCA preserve global structure. tSNE preserve local structure. So, UMAP, on the other hand, preserve both global structure and local structure. So you could see it's a powerful approach that makes it quite unique from the tSNE and PCA. So sometimes in a particular task, what I do is that I don't just do PCA and leave out. I will do PCA, I will do tSNE, I'll also do the UMAP, and then I will now settle for the one that gives me the best interpretation. So you can try all the three, or sometimes you can try one, depending on it. Again, it bounces back to choice, but like I always say, you need to beat the data set such that you can no longer be able to say, I've left this stone unturned. You have to, check there, check here, check here. So sometimes a simple task, you find yourself doing it for days or weeks. Not because you don't have a straight answer, but because you feel that you shouldn't just settle for one thing. You should do this and see what happens. Then we also talk about an example of the autoencoder, where we said this is a neural network approach where it has to compress the representation of the data. And then we would look at how we could build this using the TensorFlow or the PyTorch. Now, another thing I want to make an emphasis here is that the deep neural networks, or the neural networks we use the platform of TensorFlow, or sorry, the framework of TensorFlow or PyTorch to do them. So as we progress, I will tell you, I'd like you to install these packages, the TensorFlow and PyTorch, but don't worry, we'll get to those levels, we'll talk about them, but we will need them to be able to train deep neural networks. So, but like we said, let's keep moving gradually. So on the side of the clustering, we talk about the K-means clustering, where we said you partition the data set based on the centroids and the distance apart from the centroids. And then we talk about finding the optimal clusters will require an elbow method to find that. And then the hierarchical clustering, also we talk about how you build the tree structures or the dendrograms by continue to merge these clusters iteratively until you get to a point where you have just one global cluster. But it's a very nice approach as well. So, and again, if you are doing unsupervised clustering, sometimes you don't just do only K-mean clustering. You can also try the hierarchical clustering. But the problem is some of these things are computationally expensive. So because of that, most of the time you may not want to. But if you have that computational efficiency, then I will advise you try them and then you pick out the best approach. So the K-mean clustering, the hierarchical clustering, the DB-scan, which is in full density-based spatial clustering of application with noise. So again, we said in the case of this, we identify the arbitrary cluster shapes and isolate noise. Then we also talk about that in this particular DB-scan, if you have the large K, you are likely going to have few clusters, while if you have a small K, you will have so many clusters. So we need to find the quality of the cluster, or in other words, you need to determine what is the optimal cluster. So to do that, you will need to check out measures like the Sewage score, also this David Boudin index score and all that. And there is also another Clant something score. So there are so many ways we could be able to find the optimal clusters from these approaches. Then we also talk about, in brief, we talk about the association rules, where we say the a priori algorithms is what we use to find the frequent items that associate. And then we're also interested in like correlation in the data set. And then we said the generative models or the GANs uses the the neural networks approach to help us to find these compressions that happens in the data set. So again, we talk about the encoding and decoding in the GANs. And then the anomalous detection, like we said, is just we are looking out for the outliers, the black sheeps in the data set that you could, the data point that you could spot and say this is it. So the first thing we are going to do, like again, I said, I will always be using simple data set because of computational issues. But when we're progressing, we'll be looking at complex data set that are more tedious. And sometimes I do this so we could fast track the time so we don't have to wait for these things to run. So the first thing, the data set we're looking out for, dimensional reduction PCA example that we'll be looking at is the Irish data set. And last week we talked about this Irish data set where we say this data set is a flower data set where it has the petal, the sepal, length, and the width. So it's a very small data set. We don't have so much dimension, but it's just again for an illustration, and it's not again every time that you have to do PCA. So, my advice is when you have lots of dimensions, then it's recommended you should, try to understand how you could look at the variability in the data set. So the first thing, like I always say, you load the relevant package. So you quickly run this. Okay, so it has run. So the next thing, you load the data set, and this is the command on how you could load the data set from the skitlearn platform. So when you load the dataset, like I always say, don't just go straight to analyzing the data. Rather, always try to visualize the data to see how it looks like. So you could preview the head of the first five columns of the data set, which is the sample length, sample width, and also the target. Then, like I always say, check if there are missing values. So the df.info will help you to see if there is going to be missing values. So again, when you looked at it, you would see that there are no missing value in this case, and all of them are floats, exception of the target, which is an integer. Then before you do PCA, although some people don't do that, but I would recommend you do it because the data set most of the time are likely not on the same scale. Although these ones are looking almost like the same scale, but still you could see like the sample length is much kind of bigger here compared to this one. So if they are not on the same scale, the dominant feature is likely going to overshadow those other features. So in order for you to put them on a plain or level ground, scale them or you normalize them. So by scaling your dataset or normalizing your dataset, help them to have the privileges of starting from the same range or point. So that makes sense. That way you can be able to, even if the dataset has a small measure, you can imagine you are looking at a dataset where some were measured in kilogram, some were measured in milliseconds or something. There would be conflict because they are not having the same scale. So standardizing your dataset help you to be able to overcome this issue. So that's why you see we standardize the dataset before we start modeling here. So the moment you do that, you have them all on scale. And then the moment you also do this standardization, the dataset will move from being a data frame to becoming a NumPy array dataset. So these are all matrix transformation again. So most likely, you will define the first two dimensions in the PCA. Most of the time, the first two dimensions are what you are interested in because these dimensions are likely where you get the high variability existing, So most of the time, these first two dimensions are where the high variability. So that's why you see we always indicate 2. But like I said, I've seen a situation where they use 10. But again, it totally depends. And I would have loved us to also look at this PCA on R. But because R has this nice plot for PCA, I really love the way R does it. But anyway, let's see how it goes. So the next thing you can run the PCA by first you have defined the dimension, then you can fit it. So fit transformed help you to do that. And remember, this is the data set you are standardized. So now you could visualize how the how many of it was explained. So you can clearly see that the first dimension capture about 73%. So 73% is quite good, very, very impressive. 73, it's almost like it captures everything. And then the second PC or component capture 23. So it all makes sense because when you add them up, it's almost like you have lots of the variability captured. So the next thing you could now do is to visualize the data set. So again, you could use the scattered plot to check the visualization. So now once you fit this, it's visualized. And now you could see it did make sense. And then you can color them based on the target. But remember, in this in this particular example, is because we did have a target variable. Okay, that's why we're coloring it based on this. But in the real world, you may not have the target variable. You have to rely on maybe, for example, gender or ethnicity or something to see these different colors to see if people in one ethnicity are likely grouping are likely going to be on one side and the other, stuffs like that. So, but let's pretend that this target is not the target for supervised learning, but rather you are just trying to know the type of flowers that you're working with. So truly, you can see that, like we established last week, that the setosa stood out, but there is that overlapping between the versicolor and also the virginica. You could see truly the overlap exists between them. However, you could also see there is a good separation between them. They are not really the same, but there are some sort of overlap between these two. So, man, this is quite good separation. You could see they are clearly separated. So already from the dimensional reduction here, you could see that 3 clusters actually capture this problem, because they clearly separate very well, which makes a lot of sense. But in the real world, you will not have this clear separation. You are likely going to have a clumsy sort of clusters, and then you will be trying to look out for which ones actually partially separate. So in this case, if you do the elbow, you will see that if you go to the cluster of this, you're likely going to see that 3 clusters fit this problem very well. So the example 2 that we're going to look out for is the digit dataset. The digit dataset that we talked about last week, if you remember correctly, we talk about this is the digit data set, where we say it's an image of handwriting of data set where we have 2, 4, 3, 7, 2, 5, 7, so there is that confusion about it. For example, the way 2 is written here, it's not the same way that 2 was written here. It's not the same way it was written here. The same thing, even 1, you would see the way it was written was not the same. Even 0, the way 0 was written here was different from here and also here, and all that, even 8. So when you are trying to categorize or classify this image, the machine would likely struggle to be able to say this is a 1, this is a 2, this is a 3, this is a 4, this is a 5, because this has like 9 classes or 10 classes, so it's 0 to 9. So this becomes quite a challenge when you want to categorize them. So it is that data set that we want to look out for in this place. So interestingly, we could see that the data set has 64 features. So we want to see what happens. So when you load the dataset again, we find the shape of the dataset. So it has 1,797 rows, and then it has 64 columns. So this is the shape usually capture X and Y. So this is your X and this is your Y. And we say the X are the futures and the Y are the columns. So the futures, no, sorry, this is rows, not futures. So this is the futures. So this is the row and this is the columns. So while this would capture the label variable, that's the Y. So the next thing, we need to look at the data set before we start going to perform the analysis. So we first convert it to a data frame, and then the next thing we do is to preview the data set. And again, you could see we have this 0, 1, 2, 3, 4, and so on and so forth. So, but we have 64 features in all, including the target variable. So this is quite a large feature compared to the Irish dataset that we looked at. 64 features are quite much. So you could imagine when you're fitting these features, you're likely going to have issues around dimensionality, although it depends again on the tasks you're doing, but 64 features are quite a lot of features. So the next thing you do is the F-info to see if you have any missing. Luckily for us, for this data set, we do not have any missing, which is quite impressive. So the next thing we do is to scale. Like I said, you have to scale your futures before you feed them to the algorithm. So when you scale them, you give them a good ground for all of them to try. So the next thing is to define the PCA dimension. Now, looking at this dimension, like I said, the first two dimensions capture more of the variability. So because of that, we are always by default going to be setting it to 2. But that doesn't mean you cannot increase this dimension. But on what basis? If you increase them, you're still going to be confronted with the issues that you are running from, which is dimensional issue. So keep that simple. That's my recommendation. Okay, so when you do that, the next thing is to now see how many of the variations were explained. The first dimension explained just 12. The second dimension explained around 10. So in other words, this data, the variability was not, it did capture a lot as such. And that's because the data is quite complex. So the more complex the data set is, the more difficult it will be for you to be able to, capture this variability. So these are some of the things that, we're looking at. So anyway, remember the whole essence is to keep it simple. So the next thing is to make, fit this data to see what you have. Good. So now we have fit the data. We want to visualize the data set. So we kind of put the scale because remember there are 10. So it wouldn't make sense to start putting so we used a sort of a continuous scale. So this continuous scale makes sense when 0 is when it is very dark, 1 it's a bit bright, 2 is like that until 9, which is yellow. So anytime where you see this 9, you see this yellow. But when you look at this data set, you could see how clumsy they are. You see that it's very, very difficult for you to actually spot a particular clear separation. Probably somewhere here you could see a bit of good separation. Maybe somewhere here also had some separation, but there is lots of overlap. You see quite good overlap here. Although we did have these guys here that are also looking interesting, but this also again will be difficult when you're clustering. How to clearly get the centroid will become an issue. But you could also see, although there is a good separation, but the machine is actually struggling for it to be able to compress this. So even though the dimension we did identify was not big, but still we could see that the data set is not that easy for us to put it in even in a low dimensional space. So the exercise I wanted you guys to look at on your own is how do you still apply PCA on the breast cancer data set. So you can be able to get this data set from here. I've already uploaded the package for it. You could see this is the package for the breast cancer data set. So I've loaded the data set. So you have to follow the same approach that we did here to load the breast cancer. So the breast cancer, you load the same thing. So it will be the same approach. You load it, to be able to work with it. So in your spare time, I would like you to try the breast cancer, recreate the way we did for this digit data set, but now on the breast cancer data set. And then you see if it works fine. So we could also as well discuss the finding. So the next thing we are going to do now is to examine the data set, because clearly we could see that the linear approach doesn't fit it doesn't really address the data set. We didn't capture the variability as such the way we want. So we would like to try nonlinear approach to see, can nonlinear approach really fit the data set well for us? We'll get to see. So for you to do that, you load the right package again for the tSNE. We also again load the digit dataset, but although we have already had the digit dataset, so excuse me, we don't need to fit it again. We just need to continue what we have done. So you again 2 dimension is fine. You don't need to do lots of dimensions. So just 2 dimension is fine. Then you could see we introduced the random seed. So the random seed again is to just help us to reshuffle the data before we fit. So next we are going to fit this tSNE to see what we have. And then again, if you notice, you could see it's a bit taking time because now this is non-linear. So like we said, if you increase the complexity of the model, you will see that the time for it to analyze the data would also be much. It wouldn't be that easy. So now we are going to visualize to see what we have. Good. So now you can see PCA struggled to capture the data. Can you see how PCA looks like? This is a global structure. It clearly couldn't really find them, but can you see how tSNE separated the dataset? Can you see a good separation?
Yes.
Can you clearly see? Can you see where 0 is here? 1 was found here, and also a bit of here. And 2 was here, 3 was here, 4 was here, 5 was here, 6 was here. But you can see how tSNE separated the dataset much better than what PCA did. So this is what we mean by finding local structure. So now we're finding the local structure by kind of zooming into this global structure that PCA was able to do, but in this case, to really say, no, we can crunch the data set from another angle that does not just have to be linear. So clearly, the PCA failed because it assumed linearity, but tSNE did perform well because it's using a non-linear approach. So your own task for the exercise will be to perform this approach using the UMAP. So you would use the UMAP to see. I know you'll be asking, but you haven't seen how the UMAP looks like. So for you to do the UMAP, you will have to install the package. That's why I put the installation. All what you need to do is just to remove the hash, and then you run it, and then it's run. So, but you make sure you load the right package. Once you do that, then you'll be able to do the tSNE. But I didn't do for it because I left this one for an exercise for you. But I performed the tSNE on a different dataset called the wine dataset. Now, the wine dataset is a classical benchmark dataset from UCLA Machine Learning Repository. It comprises of around 178 samples of wines from different cultivators, from 3 different cultivators. They said each described by 13 chemical features. So these features measure such as alcohol content, malic acid, ash, alkalinity of ash, magnesium, total phenols, flavonoids, and so on and so forth. So they wanted to see, can we be able to use dimensionality reduction, such as principal component analysis, to understand the structure of this data set? Is there a certainty, or there's some chances that probably the cultivator of wine from a certain farm could cluster different from other farm and all that. So that's the essence of doing this PCA, for you to look out and see what hidden structure exists in your data set. So again, the first thing is to make sure you load the UMAP packages, so make sure you load that. Make sure you load that. So another thing now is to load the data set for the wine. And then next thing, like I said, it makes sense if you are able to visualize the data. You don't just have a preview of the data, interact with it, and see how it looks like. So the data set looks like this. You can see the alcohol, the malic acid, the magnesium. So now you could see why I emphasize on standardizing your data set, because you could see alcohol is around 14.3, 13 something, but now you have a malic acid that is just 1.7, 2.43, And then you have the ash, that is 15. Then you have magnesium, which is 127, 100, 101, 113. So if you don't standardize this data set, you will discover that you could also see the proline, which is around 1065. So if you don't standardize the data set, these large guys here will take over, and you won't have to see, we won't see this small data set showing up. So that's why we emphasize that standardize your data set or transform it so they will all have an equal playing ground, to be able to spot their contributions. So make sure you do that before you do it. So another thing is we do the df.info to see if we are going to spot any form of missing values, and also to know the type of variables we have. Luckily for us, all of them are float. We don't have an integer, which happens to be the target variable. Now, like I said, standardize the data set. So we just did that. And then the next phase is for us now to use UMAP. So you can now pick this one and make sure you can use it for this task here and see what you have. So the UMAP also, like we did in tSNE, we are going to focus on two components, which is the first two components, component 1 and component 2. And again, we are using the standardized data. So you run it. You see, it did takes time, but it's faster because remember what the tSNE does. It's looking at the global structure and also the. So again, the next thing is to run the dataset, and then we are going to be visualizing it based on the target to see what we're going to have. So good. So now you could see clearly we have three separate groups in this data set. We have this yellow guys that are mostly within the range of around 1.1. They're around 1.1, maybe it's close to 0.7, thereabout. And then we have those other ones that I have red, which are clearly within 0 to maybe around 0.5. And then we have those ones that are blue, which are around 2 point something. So maybe you could discover that this target, which could be likely the farms where these wines were produced, they are quite clearly separated. So you're having high chances of you could see that three groups actually fit in this problem very well. So you don't need to go over, creating extra ones. So it did make sense for me. It's quite interesting plot, clearly separatable. But like I said, in the real world, you may not have this clear separation. So have it at the back of your mind. But clearly, you could see that when you standardize your data set, you did quite see some improvement. So last but not the least, for the dimensionality reduction is the autoencoder. So, however, like I said, these are deep neural networks or neural networks approaches. So we will have to use the framework of PyTorch or TensorFlow. So here we are using TensorFlow. So again, before you run it, remember to remove the hash and then you run that to install it on your notebook. And also you could follow the CFD command prompt approach. So depend again on what you want. So next, after you install, you load the dataset. So again, we are going to still be using the digit dataset. So still the digit dataset because the digit dataset is pixels because they are handwritten futures. So they are pictures, and the deep neural networks does very well when you are dealing with images. So it do make sense if we use the pixel for this case. So that's why we again using the pixel. But that doesn't mean you cannot use tabular dataset. It's again depend on the problem. But neural networks generally they do very well when you are using image dataset or sequential dataset. But when we come to those topics fully, I'm going to make emphasis on that. But normally when you have tabular dataset, I will advise you to stick with the traditional machine learning approaches like the random forest, the logistic regression, decision tree, XGBoost, and so on and so forth. Those gives you quite an impressive thing compared to the neural networks. But when you have sequential data set or you have image data set, then I'll advise you to stick with the deep neural networks. Anyway, when we get to some of those points, we'll talk more about that. So the next thing is to load the data set. And then again, if you notice, you will notice I'm no longer using the standard scala. Rather, I'm using the min-max scala. And this is because I want you to understand that there are so many versions of scaled functions we have. We don't necessarily have to stick with only the we don't necessarily have to still stick with only the standard scala here. We can also use other scaling approach. But what this standard scala does is basically standardizing them around the mean, zero mean, and also one variance. However, the mean max, on the other hand, we looked at the minimum and the maximum in the data set. So they are not the same, but they are all doing the same thing. They are all scaling. But the only difference is that it looks at the minimum and also the maximum, and then it uses it to divide the actual variable. So it would be like x minus the mean or the mean divided by the max of that particular feature. Now, the good thing why I like this approach is that somehow it's robust. It's a robust scaling, although the standard scala too is also robust. But someone can argue from another point and say, but if you are doing this, you're likely leaving out the outliers. If you're coming from the mean variance angle, so the mean max actually take into account the highest in that particular variable and the lowest in that particular variable. So it does make sense for me. But anyway, you can play around with these things. They are not really something that we should create arguments around. But again, it depends on the data set you are dealing with. Most likely when you are dealing with like an integer, I think the min max makes sense. But when you are dealing with things like floats, yeah, it's fine. You could stick with the standard scala, but there is no preferential. Again, it's anything, any of them could work fine. But sometimes some of these things are just has to do with preference. So we load the data set again, we scale the data set using the min max. Then in order for you to do deep neural network, if you understand it very well, you have to shape your data set. You cannot just feed the data set like we are doing in tabular data set. But like I said, I wouldn't want to go into this thing so much because I haven't taught you guys that. But let's see if we could make a bit of example on that. Now, if you look at this neural networks here, you would see that you have to take this the data set first into this layer called the input. You have to put them into the input before you could be able to feed them to the discriminator, and then the discriminator could work on it, and then it generates and all that. So it's kind of the same stuff, so, but not like the GANs, because the GANs was talking about I wish I had an architecture of the autoencoder, how it works. Anyway, so we have the input layer. But for you to feed it into the input layer, you have to shape the data set to have a particular sort of like a pipe. It's just like when you have a window, because we consider these things like sliding of window. You don't just fit into that window. You have to position yourself in a very good direction in order for it to fit into that window. So that's the same thing with us when we're talking about the data set. We have to make it to look like a particular shape, and then we feed it. Even in the traditional machine learning, we do that, but most of the time people don't really emphasize on it. But you do it sometimes too, especially when you want to create like a pipeline in the industrial machine learning. You always have to make sure you put it in the shape that it could be able to fit into the pipeline. So that's what we are doing with the first dimension here. We'll put it into that shape. And then the encoding dimension, we put 32. Now, you could play around with this. You could use 64, you could use 16, depend on what you have. But these are just layer. So this is like this is the encoding layer. So you could increase. Another person could come and say he wants to increase another layer. You could put another layer again and put 64. Someone can, but the more you stack the layer, the more complex your model become. So, but in this case, we just want to keep it simple. So these are the encoding layer. We use 32 here. So again, we could increase it or we could decrease it. Then the next thing again that we are going to do is now the dense layer. So we have created the encoding layer, which is 32. Now, when we take the input dimension, which is this data set, we'll put it into this thing. So that's what the first this thing do to talk about the input. Then the encoded or the dense space, we will need to define it in such a way that we will use a function to help us to be able to act like a buffet or a kernel. So that's why we talk about activation here equals to ReLU. So we are in the dense function when we take this 32, this which is the first layer here, we will definitely need a function to help us to analyze those data sets because these are not linear stuff. So we need to find a way to do some transformation inside them. So that's what we are doing in these layers. So this is like in the encoding layer, you say the dense. Remember the dimension is 32 here. So when this data set is coming, you will need to project them. So the activation function will help you to do that projection. Then the decoding layer, we use a sigmoid function. So again, the decoding layer will be opening or decompressing the input layer. So that one also need another function to do that. So the sigmoid function help us to do that. So that's what we are doing with these layers. So like I said, again, you can play around with them, but for you to properly understand these things, you must have done deep neural networks. So like I said, I don't want to make a lot of emphasis because I haven't taught you guys that. So pardon me when I use some of these things. I understand your plight. Then the next thing is the auto encoder, which is now we are defining the model. So what you are going to do is to take the encoding layer that you have defined and the decoding layer, you put them inside the autoencoder model. And then the next thing you do is to compile. Then you compile. Then when you compile, you will need an optimizer. And the optimizer here we are using is the Adam. The Adam optimizer is very popular optimizer, but there are other ones that you use. And then outside the optimizer, another thing you'll be looking at again is the loss function. And here we are using the cross entropy. Now, this loss function is just like what those layers are doing is that it's fitting and then it's checking for the errors. It's fitting, checking for the errors to see what's happening. So that's what we do. Then it's when you compile, you'll now be able to, so it's just like your how do I put it? I think the simple example is when you have a frame, you package it. And then when you package it, you give it out, the person will unwrap it. So it's just like what we are doing. We package them, we put them into a very nice frame, and then when you give another person, wrap it up. So that's what some of the things does. So the next thing is to train it. So you train by fitting. And then what you're doing is that you have to use the epochs to see how many. So sometimes when the data set is large, you have to keep them in batches. So you can reduce the epoch to maybe 10 or 20 and all that. But I think this data set is not large. That's why I left 50 epoch. And then the batch size, you could use 64, you could use 32, you could use 16, and so on and so forth. Then also shuffle, just like we did in random forest. So again, don't be scared. It's still going to be the same stuff that we're doing. So the good thing about deep learning is that you have control over your model. So you can be able to reduce the layers or increase the layers, and you can play around with all those things. But don't worry, since we are not yet in deep learning, don't worry about them. Don't be scared. So you're going to fit. Now you will see it's going to take time also compared to other model. Like I said, the more complex your model is, the more it takes time. So the next thing is also we find it, yeah, we make predictions. So that's what we did. So we have already fixed it. Now we make prediction. But again, this is unsupervised learning. So we are not like setting a portion apart. But that's also a very good thing. You could set a portion apart to see what happens. But we are not setting, it's still that training set we fit, and then we make prediction on it. So now we're going to visualize to see what happens. So now we are visualizing it to see how it looks like. So this is now how the visualization looks like. You can also see that the autoencoder did not really did any sort of magic. We still have um this global structure in the data set. Although we could actually see there was this data set, this dimension here that was quite projected along the side. But generally, we did see that the global structure was preserved. But that's how the autoencoder usually works. So the same approach that we used for the other ones. But you could clearly see that though in this whole thing, I actually like the way tSNE did with the dataset. I don't know what UMAP is going to, how it's going to look like, but I think UMAP tSNE did a very good job compared to PCA and autoencoder. So again, depend on which of them you prefer. So I think for this is where we're going to